Welcome to another nice, quick, easy video. We're going to solve one of these problems, and it's going to be easy. It's going to be quick. All right, ready? So we're going to go back to our old example that we introduced at the start of the section. We plotted a direction field for this. We looked at some solutions, and it's the same matrix. It's the same eigenvalue that we found before. So immediately, right now, right, this took very little work to get here. Well, what's the general solution to this system? Well, let's look at our theorem. We have a linear system, check. With repeated eigenvalue, check. Only one line of eigenvectors, that's pretty much always going to be checked. Then this is the general solution. Let's write it down. That's great. Y of t is going to be e to the lambda t times our initial condition, e to the lambda t times our initial condition, x naught, y naught, plus t e to the lambda t times v1. What was v1? All right, we have to do a little work, but that's it. All we need to do is find v1, and we're going to be v done. So v1 is just a minus lambda I times v naught. So what does that mean? v1 a minus lambda I times v naught. A couple ways that you could calculate it, but let's just do it a little more straightforward. A is -2, minus lambda is +2, and then this is 1, this is 0, -2 again, minus lambda is +2, and again v naught is x naught, y naught. Oh, it's time for the cat to sit on the notes. Hopefully we don't need them. So what is this? What is v1? Well, this is just the matrix 0, 1, 0, 0. This is kind of a funny matrix. Well, let's remember our matrix multiplication. That's just 0x plus y naught. And then the second entry is 0x plus 0y. That's our v1. Y naught 0. And we are done. That's it. That's the solution that we found 2 videos ago, right? E to the -2t, initial condition, plus t e to the -2t times y naught, 0. That's all there is to it. So hopefully not too bad most of the time. It can get a little messier than this, maybe. I might be, we might be getting a little lucky, but you know, it's basically always just like this. Okay, just trust me. It's not much worse than this ever. We're going to do another example with a harmonic oscillator later on in this section, but for now, here's how you can see how it works. Here's how we can use the theorem. And remember what the theorem said as kind of a sort of conclusion. If v1 is 0, then v0 is an eigenvector. Okay, well, v1's not 0 unless our initial condition for y is 0. So if our initial condition for y is 0, then we have an eigenvector that's only in the x direction. Okay. And otherwise, v1 is an eigenvector. Okay, so otherwise, our eigenvector is going to be... Oh, interesting. Do you see what's happening here? If this is the 0 vector, that means y0 is 0, and this is our eigenvector. So if y, right, let me write this down, right? If y0 equals 0, then our eigenvector is just x naught 0. And if this is not 0, then our eigenvector is y naught 0. Either way, our eigenvector is just strictly horizontal, which, strictly horizontal, is exactly what we saw for our straight line solution. And notice our eigenvalue is negative. Do you think this is a stable equilibrium or an unstable equilibrium? It's a negative eigenvalue. our solutions are getting sucked in. I mean, you can see it with the vectors, right? They're all getting sucked in a quasi-spiral. All right. That's pretty cool. Nice. Anyway, that's it for this section. We'll do a little bit more in the next section about qualitative analysis. And then we do have one big example to put everything together. And then we'll finally get to the somewhat strange cases for zero eigenvalues. If you like equilibria, zero eigenvalues are going to be for you because they are equilibria abound. They're all over the place. Anyway, that's it for this video. Have a good one. Bye-bye.